Hey, what's going on Twitch? What's going on YouTube? How's it going, everybody? Welcome back to my practice stream. My name is John. Today we're going to be getting back to representation theory. This is a very beautiful subject. It is literally graduate level mathematics, and it's something that I'm learning for the first time myself. So, if this is your first time here, welcome. First off, welcome. I'm going to be studying, and I invite you to study with me. This is a practice stream, so I'm actually it's going to be boring. I'm going to be taking notes, but I'm also going to try to practice teaching this new topic to the degree that I understand it. So welcome. I hope you lock in with me, and let's have some fun. So today we are going to be getting an introduction to representation theory. I'm working through this book by Steinberg. It's an undergraduate level, like advanced undergraduate level or master's level book on representation theory. I find it quite hard because I graduated with my degree in 2012, a long time ago. I studied pure mathematics and I graduated, 14 years ago now. Then I worked in the software industry for 10 years. I worked at big tech companies like Apple, Lyft, and Google. And now I'm coming back to mathematics, and I am trying to become a high school math teacher. So I live by the idea that you can study math for fun, that there are people out there who study math just because they love it, because it's beautiful, because it's fun. And that's certainly me. I'm definitely one of those people. So, the last two times that we were in this chapter, maybe JC Maths, how's it going? Welcome, Sumit. Welcome back. Okay, so the last two times that we were in this chapter, it was April 28th, then June 9th, and now it's July 2nd. So it's about a month, or around a month, between each time that we come back to this section. So let me try to give a quick introduction to representation theory in my own words, and let's see how I do. People in chat can help me out and let me know what you all think. So the idea is represent symmetries via matrices, then use linear algebra to study the structure of symmetries. So this is the beginning, I think, of representation theory, if I understand correctly. So first, if we want to represent symmetry, what is an example of symmetry? As a kid, I think a lot of us notice things like patterns in the clock. In the clock, we have 12, 1, 2, 3, 4, 5. We have all the hours between, 1 through 12, right? ... Here's 3, here's, here's 6, here's 9, right? In the clock, you may notice a nice little pattern that if you count by threes around the clock, you'd get 12, 3, 6, 9, and then you loop, right? So this is skip counting by +3 around the clock. Of course, if you count by ones, you get every single number. If you counted by twos, 12, 2, 4, 6, 8, 10, and then you reset, right? I already did plus 3. What if we did plus 4 around the clock? 12, 4, 8, 12, right? What else? Let's try plus 5. What happens on the clock if we go by 5s? 12, 5, 10, and then what is 10 plus 5 on the clock? 5 hours after 10 is 3. 5 hours after 3 o'clock is 8 o'clock. 5 hours after 8 o'clock is 1 o'clock. 5 hours after 1 is 6. 5 hours after 6 is 11. 5 hours after 11 is 4 o'clock. 5 hours after that is 9 o'clock. 5 hours after 9 o'clock is 2 o'clock. 5 hours after 2 o'clock is 7 o'clock. 5 hours, and then finally 5 hours after 7, now we finally reset. And we go back in a loop, right? So, check that out. That's kind of cool. Okay, well, what about if we counted by 6s on the clock? 12, 6 o'clock, 12 o'clock. What if we counted by 7s? 12, 7. What is 7 plus 7? It's 14 minus 12 is 2. 2 plus 7. 9 plus 7 is 16, which around the clock is 4 hours after 12. 4 plus 7 is 11. 11 plus 7 is 18, which is 6 hours after 12. 6 plus 7 is 13, which is the same as 1 o'clock. 1 plus 7 is 8. 8 plus 7 is 15, which is 3 hours after 12. 3 plus 7 is 10. 10 plus 7 is 17, which is the same as 5 hours after 12. And then 5, let's keep it as 2 lines like the other one. 5 plus 7, finally we reset. And then we finally loop. Right? So these are all called cycles. Let's give this another color because I want to really highlight this. These are called cycles in the clock. We could do the other ones, but if we think about it, like, what if we counted how many are there in 3? Like, if you add by 3s, there are 4 in total. If we counted by 2s, 1, 2, 3, 4, 5, 6, there are 6 in total. If we counted by 6s, there are 2 in total. There are 2 numbers. If we counted by 1, well, we get all 12. If we counted by 4s, there are 3 in total. If we counted by 7s, there are 12 in total. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's cool. If we counted by 5s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ooh. These are kind of cool numbers, I think. So there's no secrets here. There's no mystery. These numbers turn out to be divisors. 4 is a factor of 12, 6 is a factor of 12, 2 is a factor of 12, 12 is a factor of 12, 3 is a factor of 12, 12 is a factor of 12, 12 is a factor of 12. Are there any factors of 12 that we're missing? I suppose 1. Yeah, we missed counting by 12 o'clock. Right? If it's 12 o'clock, then 12 hours after 12 o'clock is 12 o'clock, 12 o'clock, 12 o'clock. Right? This is just a 1 cycle. I could do the other ones. We're missing +8. We're missing +8, +9, +10, and +11. But I'm going to show one more pattern here. Let's take a look at these numbers. 12, 7, 2, 9, 4, 11, 6, 1, 8, 3, 10, 5. 12, 5, 10, 3, 8, 1, 6, 11, 4, 9, 2, 7. Do you see any interesting patterns between those two? Yeah. 12, 7, 2, 9, 4, 11, 6, 1, 8, 3, 10, 5, 12. These two are opposites. +5 and +7. They are opposites. And, well, 7, and we notice that 5 plus 7 is 12. In other words, we can say that 7 is kind of like a -5, which is pretty freaking cool. It's a loop. Yeah. We're talking about loops. We're talking about cycles and things like repeating again and again. So this is a pattern about the clock. Let's see. So if this is true in general, like, what about 8? 8 plus 4 is 12, right? So 12, 8. 8 plus 8 is 16. On the clock, that's 4. Whereas if we added by 4s... Oh, we're done, aren't we? Yeah, 4 plus 8 is 12. If we counted by 4s, we get 12, 4, 8, and then we reset. So notice that +8 is like +4 in reverse. These two are opposites. So 8 is -4 on the clock. Let's see, what else? So what I'm trying to say is that we've done all of these forward cycles, but then you could count backwards around the clock, and then that would give us +8, +9, +10, +11. And so every single cycle around the clock where we get these loops is a factor of 12, which is, I think, pretty freaking cool. So that's one pattern where cycles are popping up. What are some other cycles? Once we introduce complex numbers, we get an interesting cycle. I is I to the 1 is I squared, by definition, is -1. I cubed is I squared times I. Well, that is going to be -I. I to the 4th is -I times I. That's negative I squared. I to the fourth is positive 1. And then I to the fifth would be 1 times I. But that's exactly the same as I to the 1. So this creates a 4 cycle. This creates the powers of I create a 4 cycle, and you keep cycling and looping. Just the same, just like plus 4, plus 3 in the clock. Another example that we saw last time are the rotations of the square. If I have a square with vertices 1, 2, 3, 4, and I rotated it, say I rotated it 90 degrees counterclockwise. Clockwise. Then we get that. And then if I rotate it again 90 degrees, 1, 2, 3, 4, and then I can rotate one more time, 1, 2, 3, 4. Then if I rotate again, then we loop. So rotations of a square by 90 degrees also creates a 4 cycle. Now, what about this matrix? So first off, in some sense, I can represent the 90-degree rotations of the square with... So in math, we use this symbol to mean it's essentially the same. It behaves exactly the same as the complex number I. And same thing with the skipping around the clock. They behave just like I, where it repeats in a loop, in a 4 cycle. This 4 cycle pattern is called a symmetry. It's one example of a symmetry. Let's see. If we have a matrix that's represented like this, what happens if we raise this to various powers? A squared is I, 0, 0, negative I times itself. I, 0, 0, negative I. And this is I times I is negative 1. Top right entry would be 0 plus 0. Bottom left is 0 plus 0. Bottom right is negative I times negative I, which is negative 1. A cubed is the same as a squared times a, which we found a squared is this, and our original matrix A is this. And now I can multiply those. We get negative I, 0, 0, negative I. Oh, wait. Is that correct? Nope, we get positive I in the bottom right. So that's a cubed. Now, what about a to the fourth? we could do it two different ways. We could do a cubed times a, or I could do a squared times a squared. And I find that one slightly easier. This matrix multiplied by itself is 1, 0, 0, 1. And then if we multiply, so this is also called the identity matrix. Next, a to the fifth would be a to the fourth times a. Well, that's I. The identity matrix times a. And the identity multiplied by anything is itself. So, in other words, once again, we loop. And we get a 4 cycle. Oops. So again, a 4 cycle. Which is pretty neat. Hello, this is really useful review. Thanks. Thank you. Oh, I forgot to turn on the chat. My bad, everybody. My bad. What's up, everybody? How's it going? Yeah, so we're looping and we're finding cycles. So the 90-degree rotations of a square is, we use this word again, or this symbol, to mean essentially the same. It means essentially the same as the complex number I, and we also are seeing that it's also essentially the same in multiplication, at least, to this matrix. And that's pretty freaking cool. If you keep multiplying the number I with itself, it behaves in terms of this looping structure just like this matrix A. Now, why do I go to this more complicated matrix for the square? Well, we can study matrices with linear algebra, which is the topic that I've spent most of my streams really focusing on. We find that matrices have amazing structure, including eigenvalues and eigenvectors, where the matrix preserves something about a vector. This preserves the angle of an eigenvector. So this, again, like, we're preserving some information. We're preserving some fact about numbers or mathematical objects. And so this is some sense of structure, which is what we study when we're talking about algebra in general. Another symmetry of the square is that if I have a square, I can flip it. I'm going to write it this way. I can flip it, like, where is a square? Here, I guess. Just making sure. with this square, I mean, it's a little wavy, but, you know, you get the idea. If I have this square, I can rotate it, and these were the rotations that I was talking about before, and now we're back to the original square, right? But I can also flip it around like this. And now this is another square that's essentially the same, but the vertices have moved. Like, if we didn't label the vertices, you wouldn't be able to tell that the square had changed at all. So this is we could call it a flip or a mirror, but it's like a mirror symmetry. Okay, well, earlier we wrote out these rotations of the square. Right? What happens if I flip each of these? So these were the 4 rotations of the square, which I'll write as the do nothing rotation. Like I didn't do any rotations at all. 1 rotation, 2 rotations, and 3 rotations. And here, this square, I'm going to call it S, and it means that I flipped the square once. Another one, if I first rotate and then flip after 1 rotation, we're getting this transformation, which will then be, if I flip along the vertical line, I flip 1 and 4, 2 and 3. Then if I flip this one, I get 4, 3, and 1 and 2. And if I flip this one, 3, 2, 4, 1. Okay. So this was, first I rotated and then I flipped. I'm going to write this like functions, where I first rotate and then I flip. In this one, I rotated twice and then I flipped it. In this one, I rotated 3 times and then I flipped it. I should have mentioned earlier that, well, if you flip the square twice, then you go back to the original square. So a mirror symmetry where flipping twice brings you back to the original. And remember that a rotational symmetry, if you rotate the square 4 times, then you go back to the original square, right? Okay, so we have these. Now, can we spot any interesting pattern between these? Like, how can I get from this to 1, 3, 4 in that orientation to this one? It's a reverse rotation where I'm rotating in the other direction. So what we're saying is that we can, if we first flip and then we rotate in the opposite direction, then we get this square. And to get from, and again here, if I rotate in the opposite direction, 1 4 2 3 4 3 1 2, like, then this is a reverse, two reverse rotations. Same thing here. If I rotate in the opposite direction, then we get to 3 2. Yeah, from the left one to the right one. You can count it maybe starting from 1 2 3 4 this way. Now 1 2 3 4. It's again another reverse rotation. So this is kind of cool. I gotta lock in now. Good. Lock in. What are you working on today, Zafarib? It's good to see you, bro. Good to see you. So, we call D8, which is generated by R and S, such that R to the fourth is the identity, S squared is the identity, and RS, flipping then rotating, is the same thing as RS is SR inverse, right? Yeah, SR inverse. Oh, it's usually written this way, I think. Flip, then rotate. Yeah, if you play with trying these out, we'd also see that this is the do nothing square, the original square, and if I first flip it 2 1 3 4, if I first flip it and then I rotate, then 1 4. So I'm finding 1 and then rotating around. 1 4 3 2. So this is RS. What happens if we start with the original square, and I did a reverse rotation? So we go to this square. 1 rotates in the counterclockwise direction. And then if I flip it, 3 2 4 1, and we get the exact same relation, which is pretty neat. So this is called the dihedral group. And a group is an algebraic structure where we have multiplication. Multiplication in this case is like function composition, where you do one thing, then you do the next. And they have to satisfy these types of properties, like that there has to be an inverse. There needs, starting from one element, you need to have an inverse that gets you back to the do nothing element. This is getting a little bit more abstract, but I wanted to connect back to matrices. With matrices, we found that A, being this, behaves like a 90-degree rotation for the square. Now, we'll see that this matrix behaves like S. I'm going to put a question mark because I haven't shown this yet. This is my goal. My goal is to show that this matrix behaves like a mirror. So, if so, then squaring it should equal the identity element, because flipping twice should get back to the do nothing element, to the identity. In a group, we call the identity E, and then in matrices, the identity is I. Then in the number systems, the identity is 1. Like 1 times anything is itself. This is a aspect of algebra that keeps popping up again and again and again. 0 plus anything is itself. That's another type of identity element. Okay, so what is b squared? B squared is 0i, negative I, 0, multiplied by itself. This would, in the top left, we'd have negative I squared, which is 1. In the top right, we'd have 0 plus 0, which is 0. In the bottom left, we'd have negative I times 0 plus 0 times negative I. And then in the bottom right, we'd have negative I squared plus 0. And yes, b squared is I. So what I've shown so far is that B creates a 2 cycle. Like, remember this 2 cycle in the clock. In the clock, we had adding by 6, and we keep going 12, 6, 12, 6, 12, 6, right? Now, I want to show that in the group of the symmetries of the square, these are all of the symmetries of the square, all of the rigid symmetries. Like if I don't tear this piece of paper and like re-glue, like if I tear off this corner and glue it somewhere else, that would not be a rigid symmetry. So a rigid symmetry only allows flipping and rotating. Then these are all 8. There's exactly 8 rigid symmetries of the square. In D8, we had this relation. RS equals SR inverse. A little exercise is, note, RS does not equal SR. So D8 is not commutative. This is just like how in matrices, usually AB is not the same as BA. So this is a thing that you can show for yourself, and first do a mirror, and then do a mirror. Here, I'll write it like this. Convert 1, 2, 3, 4 to whatever the square is after applying S, and then do a rotation and see if that's the same or different than 1, 2, 3, 4 mapped to R mapped to SR, and then compare. Okay, so that's an exercise. Does AB equal BA inverse? In our matrices, I let A be rotation and B mean reflection. So let's find this. AB is, in the matrices that I chose, is this, and B was this matrix. So in the top left, using matrix multiplication, where we take a row multiplied by a column using the dot product, bro's remembering all the terms taught by the teacher. I'm practicing, dude. Yeah. I took a course in this a long time ago, and I didn't do very well in it, but now I'm relearning it and trying to do better and learn it for fun. This stuff I have a great handle of. I can teach this part of representation theory, but we're going to get into more complicated stuff. All right, so that was the top row with the first column. Now the first row with the second column, I times I is -1. I usually go to second row, first column. 0 times 0 plus -I times -I. That's the same as I squared, which is -1. And finally, we have this one. 0 times I plus -I times 0 is this. Okay, what about BA inverse? Well, matrix B was 0, I, -I, 0. And how do I compute A inverse? This is the inverse of I, 0, 0, -I. Zero I, -I, 0. We have a handy fact about 2x2 matrices, that this is 1 over the determinant, AD minus BC, times, you flip the main diagonal and you negate the other diagonal. So the inverse of this matrix would be 1 over negative I squared, which is positive 1, times flip the main diagonal and take negatives of the reverse diagonal. So, well, 1 divided by 1 is just 1. 1 times anything is itself. Let's just clean that up a little bit. 0 plus 0 is 0. 0 plus I squared is negative 1. In the bottom left, negative I times negative I is negative 1. And then in the bottom right, 0 plus 0 is 0. Voila, we get the exact same matrix in both places. So therefore, AB is the same as BA inverse. So, oops, undo that. Okay, so A creates, or it matches the 4 cycle of R. In other words, the 4 cycle means R to the 4th is the identity. B matches the 2 cycle of S. S squared equals E. And A and B multiply or combine the same way as R and S. That RS equals SR inverse. Therefore, these two matrices behave just like the symmetries of the square. And we say that A and B, these matrices, represent the symmetries of the square. Because, bro, you are literally a good teacher. Thank you. Thank you. Awesome. I'm very proud of that. Thank you very much. I appreciate that. Because this is some really beautiful, really cool mathematics that I think that somebody can teach to a middle schooler. Like, even if it requires just a little bit of extra stuff, you need to define matrix multiplication and other things. But you can, I think that that's actually really interesting. Heck yeah, man. Heck yeah. Right? So let's recap back to where we started. We started with the clock, and we found these patterns in the clock that if you counted around the clock by 3s, you get stuck. You never see 1 or 2 or 4 or 5. You get stuck. 12, 3, 6, 9, 12, 3, 6, 9. If you counted by 2s, you get stuck with all the even numbers, right? These are 6 cycles. These are 2 cycles. We found cycles in something that we have. We found cycles in the clock, which is a kind of pattern that at least I remember I noticed, and I was like, oh, that's nice. Like, you get stuck in those. You never see the other numbers if you keep counting by threes. Another example that I wanted to briefly mention is like in music, this is like scales. Scales are 7 cycles. That there are 7 notes. For example, A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7, and then you loop back. If we call one note A the same in some sense as another note A, then yeah, dude, like this creates also a 7 cycle. We can also count around with the circle of fifths. And I believe that this creates a 12 cycle. And it would see all of the notes, including A sharp, C sharp, D sharp, F sharp, and G sharp. If we count in fifths, we get all of these notes. So 7, 8, 9, 10, 11, 12. Yeah, you would get every single note in Western music. Cool. So this is all some patterns about symmetries and the beginning of representation theory. So in linear algebra, we study matrices with eigenvalues and eigenvectors. We also study things like orthonormal bases, or in other words, orthogonality. These are like two of the main big structure preserving tools that we have in linear algebra. So we could ask, what are the eigenspaces of A and B? This is a question that we can ask ourselves based on everything that we've learned so far in linear algebra. We could also maybe ask about diagonalization with orthonormal bases and converting to an orthonormal basis for each of these two matrices. But we have a lot of tools in linear algebra, because now I took something that was abstract. It was quite different than the type of math that we usually study. Like with this kind of math, I need to create special equations like these, and at least with the square I can draw it. I can draw the vertices, but it's more abstract. It's weirder, and it's not regular numbers that we can multiply, and it's not as familiar as the complex numbers or the real numbers. But by finding another mathematical object that's easier to study, which are the matrices, we can see if there's any patterns that we can find with these matrices, and then say that there's similar patterns in in the abstract group. So, thanks. Okay, let me read. Let me catch up with chat. I think that this is my introduction today for representation theory, and I think it's getting a little bit sharper. And we started from something that's very familiar. And we went to things that are like a little less familiar. This one would have been even better to show that -1 squared is +1, right? This one is a 2 cycle. Just like this 12/6 loop in the clock. Okay. So here is my intro to representation theory, also kind of intro to group theory. I think it's nice to try to introduce both together. Let's see. What's a good spot to... let's leave it right here while I answer chat. How's it going, everybody? How's it going? Bro, you're literally a good teacher. I appreciate it, dude. Please don't make your persona M. I don't know what you mean by that. Personality related to maths. I love math. Why would I not make my personality... You mean like my identity? No pun intended. Like, don't identify with math too much. I think it's a good thing. And I mean, I'm not just a mathematician. I am also like a guitarist. I'm also a software engineer. You know, I'm also a loving husband. There's lots of things that I am. It's not just math, obviously. But I do want to teach math because I like it. I enjoy it. I study math for fun. Like, usually people only study this if they want to become a mathematician and invent new math. I don't really want to invent new math anymore. I used to want to invent new math, but not anymore. I've seen your interviews. You think too much of normal talks that is harmful to you, my bro. I don't know what you mean by that. What do you mean? You think too much of normal talks that is harmful to you. You are so down to earth apart from previous talk. You mean like... Also, by the way, Meowth, what a name, dude. Pokemon reference? You were very smart like that person? No. I think maybe you meant Einstein? Did you mean Einstein, dude? So are you reading YouTube chat or only Twitch? I'm reading YouTube chat. I am reading YouTube chat. In fact, I only have one person watching on Twitch, and they're not even chatting. So, yeah, I'm primarily here on YouTube. I'm just catching up on the old chat. Let's go. Music note, concepts on the way. Yeah, it's cycles, it's patterns, it's symmetry. I'm fed up of Indian education system, only rote memorization. I'm sorry to hear that. Concepts are what I find beautiful about math, like the reasons why math is true. I find that really interesting and motivating and beautiful. Just memorizing facts is not very interesting to me, personally. What's up? How's it going? Everybody else? What's up, Pumpkins? Good to see you, bro. You're on the right path. This method is called the blurt method. What is that? I've never heard of it. Oh, yeah, Prism. Yeah, I'll do discrete mathematics here and there. I won't focus on it all the time, but yeah. Yeah, I'm a software engineer. I could answer some questions here and there, for sure. Hey, Prism, you don't have to retract your messages. You don't have to, yeah. Um, yeah. 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 Yakubijan, I don't think that was relevant, so I'm gonna remove that one. There's a lot of gap between P and N. I don't know what you mean. Oh, yeah, the Einstein typo. Okay, blurt method means writing all the things on a blank page to remember it for your whole life. Yeah, exactly. Like, I tried to give a little lecture. I tried to give a little introduction to this topic from scratch, from a blank piece of paper. And that's an excellent way. Like, not just write down on a blank piece of paper everything that you know, but also teach it as well and explain it to somebody else. That's another step of learning, I believe, and mastery. Um, that's another way to try to make sure that you learn something well and that you can remember it your whole life. Okay, so I think I'm all caught up on chat. Nice to meet you all. I see we've got a few new faces, a few new names. Okay, so here's a little bit about what the book, how it introduces representation theory. The book points out that most people's first introduction to abstract algebra is via vector spaces. Vector spaces is when math starts becoming a little more abstract and we start studying algebraic properties of more abstract settings. And to me, this is where math really became much more interesting and much more fun to me. So this person says that somebody can learn representation theory of groups before more complicated representation theory. And this is the approach that I am taking. Groups capture symmetry of objects. Group representation theory can be motivation for module theory. Group representation theory is actually useful. Like group representation theory, where we represent symmetric things. Like another type of symmetry is things like crystals, for example, in physics. And lots of other examples in physics, like string theory is 11-dimensional mathematical space, and it involves lots of symmetry. Physics is really, really based on these ideas of symmetry. So there's not too many intro books. So this person wrote a book. It omits some more modern version, a refactoring of this topic, and it focuses on the Fourier analytic approach. I'm looking forward to learning what that means. Crystals come under chemistry? Yeah, maybe. I don't know. Yeah. But isn't chemistry just applied physics at the end of the day? For you, the abstraction starting point was group theory. Totally. Yeah, I mean, for me, vector spaces... But you said that you didn't take a full linear algebra course, right, Lockheed? Because, I mean, if you just study matrices, yeah, it's very concrete. It's not very abstract. But linear algebra, which is the study of linear maps and linear transformations of vector spaces, that, like, vector spaces is a much more abstract concept. And at least at my university, you had to learn vector spaces before you learned group theory. Everything is applied maths or applied philosophy. Yeah, I studied math and philosophy. So to me, everything is just applied math or applied philosophy. Yeah. Okay, so here's some more introduction. We're going to learn about something called the Burnside's PQ theorem someday. and this is the first triumph of representation theory. Non-abelian groups of order p to the a, q to the b cannot be simple. I remember something from abstract algebra that connects to Galois theory, simple groups, and solvability versus groups that are simple can create quadratic, cubic, and quartic equations, but the fifth Sn or S5 is not a simple group, so therefore there's no quadratic equation for the fifth degree polynomial. There's no solvable, there's no single equation that you can write down for a fifth degree polynomial. The rest of this is some examples that apparently representation theory can be applied to engineering, sound compression, probability, for example, card shuffling, diffusion processes, data analysis, graph theory. Apparently, representation theory is also related to Will Smith eating spaghetti. Dude, that's kind of cool. Okay, and in the past, I've done this introduction to group theory a few different times, a few different ways. Today, I introduced group theory with matrices and the matrix representations. Okay, so there's our intro. Now, let's go back to my favorite subject, linear algebra, again. My only exposure to linear algebra was matrices from high school, and you went straight to group theory. See, that's where you made a mistake. That's where your teachers made a mistake. They should have taught you vector spaces before group theory, I feel. It's so useful. Vector spaces are so beautiful, and I think that they're a good introduction, to getting your feet wet with abstract algebra before going as abstract as group theory. Although group theory is beautiful. Group theory is really beautiful. Okay, so today is not June 9th. Today is July 2nd. I'm not going to track how many times we've hit this section. All right, so we've done this exercise, I remember. Today's exercise that I want to try to see if we can make any progress on, and the rest of the stream is going to get a little bit more quiet and a little more locked in study-like. Degree 5 not solvable in a nutshell, A5 is simple. I remember, I was going to say it relates to A5, the alternating subgroup of Sn. But I didn't want to misspeak. I would love to study Galois theory here. I feel like I never really learned Galois theory very well. So, section 2, exercise 3. This is the exercise that I want to work today. And it's a review of linear algebra. Let V be let's give ourselves a little more space. So in the proof of a proposition, we defined v hat as v e1 e1 plus dot 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 v en en. So where e1 through en is the basis for vector space W. Did they use E or W? Because I kind of am now thinking that this should be W. No, okay. Yeah, where EI, the important thing is that it's an orthonormal Okay, so let's redefine that. Prove that if W is another vector in the subspace W, the norm of, or the distance between V and V hat is strictly less than the distance between V and W. Deduce that V hat is independent of the choice of basis, the choice of an orthonormal basis Okay, this is our exercise, and this is the most important part. We want to show that the distance between V and V hat is the smallest possible distance for any vector in W. Hey, and Stucky is in Twitch. How's it going in Stucky? I don't know why my multi-chat isn't working yet. I should, Stream Elements should be mixing chats together, but doesn't seem to be working yet. So why is that? Super annoying. Yeah, I don't know. I just don't know. I thought that it would be mixing the two. What the heck? Okay, I'm very confused. about how to use stream elements. I suppose it doesn't matter. Aha. The different accounts. I can't connect them? Okay, whatever. Doesn't matter. Current linear algebra knowledge is still pretty bad. It's just a specialization of category theory knowledge to the category of vector spaces. See, you gotta learn some linear algebra, man. Without, like, forget about category theory and try to work some linear algebra problems with me. Bro, guitar videos are goated. You like them? Yeah, man. Hell yeah. I'm glad that you like them. Bad Streamlabs bad. I'm using Stream Elements, actually. Maybe I should be using Streamlabs, though. I've heard that Stream Elements might be shutting down, and I should switch to Streamlabs. I just do not care enough. I don't care enough. I've somehow hacked together something where chat is showing up, and I don't want to mess with it. Hey, Religion Slayer, what a name. Yeah, I mean, I'm always happy to try to help with specific questions about the JE, but I don't really want to make like JE prep videos because it doesn't really help me. Like, I don't really find that fun, so it's not really a hobby for me, and I don't think is really going to be the best way for me to be practicing teaching in America. So, yeah, matrices are kind of boring. That's fair, and it's because high school ruined matrices for you. That's a shame. Yeah, I took down that video. I don't really like that video. Somebody else made that edit. I don't really like it very much. And yeah, you can learn linear algebra without matrices. Dude, that's an important thing. Like, they kind of come up, but you can study, like when you're studying vector spaces, you're not really studying matrices as much. Like, there is some, but like coordinatization of linear transformations, which is super important. Like, that is super, super important. Okay, so this is my goal. Let's begin by focusing on prop 223. And this is going to maybe help me illuminate a path to working that exercise. So proposition 223, here's some legit real linear algebra for you. So prop 223 says, let V be an inner product space and W be a subspace of V. Then there is a direct sum decomposition V equal W direct sum with W orthogonal. Okay. Let's see what I can do on my own, because I read this a couple days ago. Yeah, you gotta learn vector spaces and linear algebra before you try to learn module theory. That's, yeah. Ah, man, yeah. Like, after you learn vector spaces, then that motivates module theory. But you should still learn linear algebra on its own before learning the more abstract stuff. Okay. Recall that W perp is the set of V in V such that V dot W is for all vectors in the subspace W. Like, it's a set of all orthogonal vectors to W. Dot product equals 0 means that V is orthogonal to W. The angle between them is 90 degrees. Okay, so we have that definition. And what does this direct sum mean? A direct sum B is A A direct sum with B. Here, wait. And if V is the direct sum of two vector spaces, subspaces, then for all V and capital V, then that vector can be split as V1 plus V2 for a vector in the first subspace and a vector in the second subspace. And on top of that, that the only vector in common is the 0 vector. Let's see. Thus, for any V in V, we want to find a W in W and a W perp in W perp or U or something in V without W, such that V equals W plus U. I know what the projection should be, and we're going to notate it with V hat, and this is going to be for each EI this is a scaling of a basis vector of W, so it is in W. So V hat is clearly in W because we're adding scalar multiples of the basis vectors of W, where the set EI is an orthonormal basis. Can I just say, then let the other vector be V minus V hat. So then pretty much by definition, V is V hat plus V minus V hat. We want to show so U is V minus V hat, U is V minus V E1 E1 minus dot 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 V E N E N. Is this going to get us anywhere? How do I show that this is not in the subspace W? Like, we want to show that U is not in capital W. Can I get there from this? This is one goal. And we also want to show that U is orthogonal to V hat. In other words, U V hat. The inner product of U and V hat is 0. I think two vectors are orthogonal either option here. Like, the first line is true if and only if the second line is true, because the complex conjugate of 0 is 0. So we can just show the second line. V hat U. Oh wait, no, V hat and Yeah, v hat and u, I have defined as v hat and v minus v hat, which is v hat, comma, v minus v hat, comma, v hat. Oh wait, v hat, inner product of v hat and v hat with itself. Man, I don't know. This is now a basis spawned out of nothingness. Yeah. The Design of Everyday Things. It's an excellent book. How are you reading these books? Are you like doing like an image lookup or something? How are you finding those books? Yeah, you were built reversed, exactly. Sriyan, hey, I'm back. A lot of things are going really well. I'm happy to hear that. Good luck. Good luck, dude, on the JE. Good luck, dude. Thanks, bro. Thanks, Sriyan. I appreciate that. Okay. I'm going to give up early. Stuck. I'm stuck. Let's read the proof. I don't want to spend too much time. Maybe I'll be able to... I think I might be able to get it if I stared at it a bit longer, but for the sake of YouTube, I do want to just take a look at Steinberg's proof. First, if W is in W intersect W complement, then the inner product of W with itself being 0. Why are we doing that? Why do we know? First, if W is in both of them. Oh. Yeah. Because that's the definition of W perp. This is a set of vectors such that phi.W equals 0 for all W in W. Implies that W is equal to 0. This is part of the definition of the inner product. This is an axiom in the inner product. So that's one thing. That implies that W is 0, so W intersect W perp is identically the 0. The only element in the intersection is the 0 vector. Next, let V be a vector in vector space V, and suppose that E1 through EM is an orthonormal basis for W. Put V hat equal to, so I got this part right. I may have used EN instead of EM, but put V being that and Z. Okay, so I got this key idea correct. We define V hat and we define the other vector, which they call Z, and I was calling U. Then V hat is in W. They just say that. Then V hat is in W. I showed that part, right? I got, whoa, a basis spawned out of nowhere again. Yeah, axiom of choice, right? Finite dimensional vector spaces always have a basis. Isn't that equivalent to the axiom of choice or something like that? Okay, so I showed this sentence briefly, but it's somewhat clear. We claim that Z is in W perp. Okay, so I had the general structure, the basic beginnings of this idea, because I came up with, I defined the orthogonal complement. We know that later we know that we call it the orthogonal complement. And then we define this other vector so that V is equal to Z plus V hat. And then we claim that these two must be orthogonal. Okay, to prove this, it suffices to show, to show that Z is orthogonal to every basis vector. Okay, this is a bit better. Right, so we want to show that Z is in W, in the complement of W, or in the W perp. I was trying to show that Z is orthogonal to W perp. V hat. I was trying to show that Z and V hat are specifically orthogonal, but we want to show that Z is orthogonal to every vector in the complement. And to do that, we show that it's orthogonal to every basis vector, because if it's orthogonal to every basis vector, then every W is a combination of the basis vectors. So if we can use linearity then to say that this would be equal to A1Z E1 plus ... AM ZEM. So if Z is orthogonal to every basis vector, then all of those inner products on the right-hand side are all 0. So then the inner product on the left-hand side is also 0, right? I am in my late 30s. Take care, Levi. Good to see you, bro. Good to see you, dude. Also known as null vectors. They have dot product with themselves equal to 0, but are non-zero. Then that you're defining something called a dot product that is not in an inner product space. Like the definition of an inner product requires that the definition of an inner product requires this. So what you were describing is something that is not... Ooh, interesting. Special relativity's metric is not non-degenerate. Wow, interesting. So special relativity is not working with inner product spaces, but something else. I haven't seen it. That sounds really cool. Wow. So here's the reasoning. Here's the details on that claim. Like, why does it suffice? And now this is a much, I think, easier thing to show. To this effect, we compute, I like that phrase, to this effect. Z, E, I. They skip this intermediate, but I'll include it. V minus V hat E I is equal to V E I minus V hat E I. Why? Aha. So, I see it. They say this because the set E of EI is an orthonormal set. So this step is what I want to fill in the details on. V hat EI is equal to remember that V hat is defined as VE, the sum of these scalings of the basis vectors, projections to each of the basis vectors. So then, by linearity, this is going to be V comma E1 times E1 EI plus dot 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 V right? And this is exactly equal to VEI because EJ is equal to 0 or 1 if I is equal to J, or, if I is not equal to J or I is equal to J. So all of these are 0 except for the EIth term. Yeah. Okay. There's just a little bit of details filling in why these two are equal. And now we have the dot product of Z and EI being 0, and then therefore, so he doesn't say this, but therefore Z is in W perp. And then he says as V is equal to V hat plus Z, it follows that capital V is W plus W perp. And this concludes the proof. He says that and draws the cute little square, which is almost kind of redundant. But yeah, there we go. There's the full proof of this thing. So the key idea, I got the main gist of this idea. He just used Z instead of U. And this was close, but what I really want to show is that I want to show that Z is in W in the complement of W, i.e. Z for all vectors in the subspace, Z is orthogonal to every vector in the subspace. This is true if and only if Z and EI and then we run through the calculation. Cool. So I got something fairly close, but we got a bit stuck. There's the proof of that proposition. So that's the main key idea. Hey, how's it going? Malcolm, my brain hurts. This stuff looks like matrices, but it isn't. Yeah. We're talking about linear algebra, actually, like a more abstract form of linear algebra where we're working in a more abstract space, but it is matrices. And I know you weren't here earlier, but the goal right now is to study representation theory. And what I showed earlier is, have you ever heard of Malcolm? By the way, let me know on Twitch if you're still there. I just saw your message. Symmetry at the beginning of this stream, I defined what symmetry, I gave some examples of symmetry, like counting numbers around a clock creates a cycle. And we have various different cycles, like counting by twos or counting by sixes, counting by ones, counting by fours, counting by sevens. Those all create cycles. In music, we have 7 cycles in our scales. The circle of fifths creates a 12 cycle. And then we have other more familiar cycles, like -1 times -1 is +1. And then you keep going back and forth. +1, -1, +1, -1. In the complex numbers, we get a 4 cycle of I squared, I cubed, I fourth, back to I squared, I cubed, I to the fourth. This creates a 4 cycle. And then matrices, I showed that this matrix behaves just like I in that it creates a 4 cycle. A squared, A cubed, A to the fourth. A to the fourth gets you back to the identity, and then we reset and we come back. So I'm trying to show you because you said that this stuff looks like matrices, and that's not an accident. Really, we are trying to study symmetries with matrices. We're using matrices to study symmetry. If you've ever heard of the dihedral group, I showed at the beginning of the stream all 8 symmetries of the square. Where did I put it? Where did I put my little... I had a nice... Here it is. Here's a nice little square. You can't see it too well because my camera is zooming on my face. But 1, 2, 3, 4, you can label the vertices and you can rotate this square 4 times and then you're back to the original square, right? You can also flip the square and then you keep cycling back and forth like that. And then you can combine those. You can flip and then rotate. And then we get all of these 8 symmetries of the square. We also find a relation, like if you flip first and then rotate, it's the same as doing a reverse rotation and then flipping. And then I showed that these 2 matrices behave just like those symmetries of the square. You can combine them, like first A creates a 4 cycle, B creates a 2 cycle. Here's that proof. B squared is the identity, and then so we loop IB, IB, IB forever. And then we can combine those 2 matrices in the exact same way. So I showed that AB turns out to be this, and BA inverse turns out to be this, the same matrix. So A matches the 4 cycle of R, B matches the 2 cycle of S, and AB combine in the same way. So these 2 matrices have the same structure as the more abstract symmetries of a square, which is a more abstract mathematical idea with something much more concrete and understandable of matrices. So, not gonna lie, I hate the words calculus and linear. It's math. All of it is needed to do all of the other stuff. That's true. Yeah, all of math is interconnected. Math is all math. Math, you use calculus and linear algebra in different fields, and we create different types of math. And different types of math are like, well, what happens when you combine a bit of this and a bit of that? What math do we get when we combine calculus and linear algebra or something? What's up? F Life, how are you? Fook Life, what a name. How's it going? Welcome to my practice stream. My name is John. I am a math practice streamer. I'm just sharing my study sessions. Though TBF in Europe, we mostly just learn maths. Cool. And only once you get super specialized, the teachers are like, oh, by the way, this is algebra. And we look at it and we don't see the difference to normal math. Nice. Yeah, you saw that and your brain went to, oh, this looks like matrix indices. Yeah, so that might have been a coincidence, but the topic that I'm studying right now, the inner product, what you just pointed at, I'm looking at the wrong page, aren't I? Review of linear algebra. Am I just working on the wrong page? Where did I put it? Oh yeah, these pages are early. Oh well, so you were talking about this, like these inner products. This notation, like bracket XY, this is an abstraction of the dot product. Have you learned the dot product of two vectors? So this would be x1, y1 plus x2, y2 plus ... xn, yn. You probably have if you've learned matrices, because this is how you calculate matrix elements. But yeah, this is an abstraction. This is the more general form of the dot product. The dot product is a special inner product. So yeah, what you noticed being like matrices truly was, like, this is very similar to matrices. Calculating the dot product, like if I have a matrix A and another matrix B, then we get a third matrix where one element, Cij, is the dot product or the inner product of row I of matrix A and column B of matrix B. This is like calculating each of those elements of a matrix. Yeah. Non-zero. Where did I get non-zero? Oh, your age is non-zero. Yeah. And Leo is all of our friends. Yes. Leo is a friendly guy, and he's our internet math friend for sure. Yeah, so it was matrix indices, but weird because other maths. You thought this is a matrix, but not. It's like a matrix if it wore a dress. That's funny. Okay. Yeah, I guess so. I mean, it's just a different... It looks a lot like matrices because we're talking about indices I and J. It's very similar to matrices. This is like an abstraction of matrices. Okay, so that was a proof about this proposition that any inner product space can be decomposed into orthogonal subspaces. So now I can return back to this exercise and see if we can make any more progress on this. I'm going to copy this whole exercise and try to work this on the last page of this notebook. Okay. I don't I don't know if I have time to really try to prove this, but let's see what we can do. All right, so let's recall V is an inner product space. W is a subspace with an orthonormal basis EI. An ortho B. So that if V is a vector in V, the distance between V and V hat is strictly less than V minus W if W is not V hat. This is what we want to show. So, generally when we're working with norms, it's easier to work with the square of a norm. And because... Why are we doing that? First, the norm of x minus y... Oh, wait, no. The norm of x is equal to the square root of x inner product with itself. And so the norm squared is equal to the inner product of x with itself. Then because x, the inner product is non-negative, then because the inner product is non-negative, that is one of the axioms or properties about the inner product. If how do I say this? We can work with the square of the norm. Like, yeah, we can take square roots. And we get one solution. Every time that we take square roots, we can convert back to the norm of the vector. So it's generally much easier to work with the square of a norm. Now we have this. Oops. Well, what happens if we add and subtract? The distance of V and W. I mean, that's one approach. Another is that we always have this triangle inequality. So could also do this. And V and W yeah, V and W, this is strictly greater than 0 because V hat, W is assumed to not be V hat. But now my inequality signs are kind of pointing in the wrong direction. They're not combining the right way. we want v minus v hat strictly less. My goal is v minus v hat is strictly less than v minus w for any w not equal to v hat. So I started with v minus v hat, and we found something here, but now this is, we've gone too far with this. We've overshot what I want to show, because the distance between v hat and w is greater than 0, whereas I want this distance is strictly less than this other distance. So that algebraic approach does not work out. V minus v hat. Isn't there some other fact about isn't there some way to show that this is greater than something else? It's not quite as simple as this. I want to say it's something like the absolute value of that difference. Is that true? Yeah, this goal is totally somewhere it's triangle inequality. And I think it's like this like reverse triangle inequality or something. There's some fact like this that I want. Never mind, I'm stupid, ignore that. Yeah, you got it. You found it, right? Because this is some epsilon, which is positive, but I want to go from there strictly less than, like, I can't continue from this point, right? Like this inequality on the right hand side I've already overshot, you know, this goal. I think that this is something called like a reverse triangle inequality. Let's ask ChatGPT. I've seen this in a book somewhere. Okay, yeah, I got it. So I got it correct. We got to wrap this up soon, but we're close. We're super close. Fook Life, that's awesome that you're trying to learn math from streamers. That's great, dude. Great to hear. So absolute value of x minus y is greater than or equal to Oh, I meant the greater than or equal sign here. So but now we'd be starting with a greater than sign, so I should work with the other option. We know that this is greater than or equal to the absolute value of v minus the absolute value of w. But somehow I need to get v hat in here, right? So v minus w plus v hat minus v hat. So I know that this is some positive amount because v hat and w are not equal. Yeah, the inequality goes the wrong way again, right? See, I keep feeling like, oh, it should just be one of these triangle inequalities, but there's got to be something a bit more, right? Because, like, again, we're subtracting a positive amount. Like, yeah, right? I don't think that this is enough. I mean, I really think we need to use something about the definition of what v hat is, I think. So I really feel like converting this to using the inner product, which is the square of the norm, is the right way. So starting from the left-hand side, yeah, I don't know. I'm getting stuck on this thing, man. Do you think that there's a math category in Twitch? I couldn't find a math category, no. I figured that co-working is a much bigger category. I don't know. Maybe I should try. Maybe I should try again. There was like, good question. Fluke life. Let me check again. Maybe there is. Yeah, I always feel like I'm not really great at these like norm questions and like distance metric questions. I always struggle with these, dude. Okay, can I change? Is there a math category? Oh, there is. There's math with 2.6K followers. Okay. I mean, it calls it a puzzle and educational game. Yeah. Okay, let's try it. But I gotta go, actually. We've been streaming for 2.5 hours. I'm stuck. Oh, you got it? Nice, dude. Here, drop your solution in the Discord. Take a photo or, use LaTeX or whatever. Because I really gotta go. You apply norm on both sides of the equality and then do triangle inequality. Okay. I really gotta go, though, unfortunately. Bye. I gotta go, everybody. Bye. I gotta go to the bathroom. Bye.